Okay, so Democritus was a philosopher, right? So he knew a lot about a lot of things, but he had this specific idea about the atom, or about matter in general. Okay, he said that all matter was divisible, okay, or it can be broken apart. He said that all matter can be broken down until it reached the most basic unit. And once it reached that most basic unit, or the smallest unit, then it is no longer divisible. Okay, it cannot be broken down past this most basic unit. Okay, he named this most basic unit, or the smallest unit, the atom. Okay, because in and of itself, it means indivisible. Okay, so he said we can break down matter, break down matter, and break down matter until we reach this small particle that can be broken down no more. We're going to call that the atom. So Democritus taught this theory and preached this theory, but nobody believed it. No one understood the fact that we could break down matter until a certain point, and then it's no more. Okay, he wasn't believed. He wasn't very widely trusted or believed on this theory. Okay, so this was Democritus. He said that all matter can be broken down until a certain point, until we reach the atom, and then it can't be broken down any further. The next philosopher, the next scientist, was a guy named Aristotle. He had a very different theory on matter. He said that matter was a whole, and it could never be broken up. It could not be broken up into smaller pieces. He said that everything in the earth was made up of these 5 elements. Have you heard of Aristotle's 5 elements before? Yeah? Good. So there's 4 of the main ones that you hear a lot, and then there's this 5th, ether or aether, however you're going to say it, that encompasses something else. So people believed Aristotle and his theory that everything in the earth was made up of these 5 things. Right? We can't break them down. It just consists of these 5 things. He was very widely believed. Once we hit the late 1700s and scientific discoveries were becoming more and more common, by the time we reached the 1700s, we knew what an element was, right? It has very specific chemical properties. An element, this is another review of your definition of an element, so if you already have this down, you don't have to put it down again, but an element is a substance that cannot be broken down by ordinary means, right? Elements have specific chemical and physical properties that cannot be broken down any further and retain those chemical or physical properties. Okay, so we know now that we can break an atom down, or an element down into protons, neutrons, and electrons. We can see those individual parts, but they no longer contain the physical and chemical properties of that element. Does that make sense? Okay. By this time, we also had somewhat of an idea of what a chemical reaction was. Okay, we understood that new substances could be formed, or substances could be transformed into something else. There could be a color change. All these different things gave us a clue that there's some sort of chemical reaction going on. So we had an idea about what a chemical reaction was at this point. Okay, when we transformed into a new substance. Okay. Into the 1790s, so the later part of the 18th century, we can see that scientists start looking at basically the quantities of these chemical reactions. Quantitative nature means we want to know the amounts of our substances that were used and the amounts that were created. Okay, so we knew that we could combine 2 things and undergo a chemical reaction. Now we want to know how much of our product is being formed, or how much did we use and how much got used up, things like that. They wanted to get more and more specific. Okay? So the quantitative comes from the word quantity, right? We want to know how much of our substances are being used or being made here. So this led to the law of the conservation of mass. How many of you have heard that term before? Good, very good. You should have heard that term. And what does the law of conservation of mass mean? Yeah, Jack. Perfect. Matter cannot be created or destroyed. So mass or matter here mean the same thing. Okay? Mass is neither created nor destroyed during ordinary chemical reactions or physical changes. It only changes form. Okay? So you can put that down in the short little snippet form, right? Mass can neither be created or destroyed, or you can include the long form here if you wish. Throughout every trial that they went through, they started to understand that what I put in is going to come out, right? In terms of mass. It might be in a new substance, but it's not going to be created or destroyed here. It's either going to change forms into something new, or it's going to come out the other end. Okay? So throughout the trials, they also led to this law called the law of definite proportions. Have you heard this one before? Some of you, yeah, okay. Law of definite proportions tells us a chemical compound contains the same elements in exactly the same proportions, regardless of the size of the sample or the source of the compound. So that's a lot of words for a pretty basic definition. A compound contains the same elements in the same proportions always. Okay, you can kind of cut it off there if you want. A chemical compound contains the same elements in the same proportion always, in order to be considered that compound. So here's a couple examples here. Sodium chloride is always NaCl. If it's NaCl2, it's no longer sodium chloride. It has a different name, right? If it's Na2Cl, it's a different compound. Okay, that doesn't work. But if it takes on a different ratio or a different proportion of those elements, it's a new compound. It's no longer sodium chloride. Okay, so sodium chloride is always 39.34% chlorine and 60.66% sodium by mass. So if you're looking at this compound, the ratio of sodium to chloride should always be the same. No matter where that salt comes from, in order for it to be called sodium chloride, it has to be NaCl. So it's 30% chlorine and 60% sodium. If you take a sample of that, whether you have 10,000 10,000 salt compounds or 2 salt compounds, 39.34% of it's going to be chlorine, 60.6% of it's going to be sodium. Okay? So what is the chemical compound for water? H2O, right? So water always has 2 hydrogen atoms, 1 oxygen atom. If it becomes H2O2, what compound does that form? Anybody know? Hydrogen peroxide, which is not something as friendly as water, right? So that ratio change makes a huge difference. So water has to be H2O. Okay, and we can calculate its percent by mass there also, but it's always the same ratio, always the same elements. If it becomes CHO, takes on a whole new compound, all new properties, all new everything, okay? So compounds have to be same elements, same ratios, or proportions. Okay? Scientists knew that elements can combine to form more than one compound. So basically what we're saying here is we can take hydrogen and oxygen and we can arrange them in a way to make water, or we can take hydrogen and oxygen and arrange them in a way to make hydrogen peroxide or hydroxide or lots of different things. Okay, so if we look at carbon and oxygen, for example, it could form CO2 or CO. Those are 2 different gases, right? Carbon dioxide or carbon monoxide. So this kind of principle here is called the law of multiple proportions. So we have the law of definite proportions, and now we have the law of multiple proportions. And this is what the law of multiple proportions is telling us. Compounds have to be formed using whole atoms, right? Whole atoms. You can't have H 1.5 to O, right? You can't take out 1.5 hydrogen atoms. So they have to be combined in whole numbers, and they can be combined in lots of different ratios. of an atom. So even though this is the same ratio here, 2 to 1, right? 2 to 1, that's the same ratio, but it's not the same compound. This does not give us anything. We can't have half of a carbon atom combined with a whole oxygen atom. Does that make sense? So even though the ratio is the same, it has to be in whole numbers. So these subscripts here always have to be whole numbers. We can't ever use fractions. Hopefully that's a common sense type thing. So he said matter is composed of atoms, and only whole numbers of atoms can combine to form compounds. So like we talked about the law of multiple proportions, we can't have fractions of an atom. Does his theory on the atom agree with Democritus or with Aristotle? Democritus, right? Aristotle said there's only 5 elements. Democritus said we can break things down until we reach that atom. And this is what Dalton was saying as well. So his theory is a few different points, and everything that is going to stay in black ink means that it's still true today. When I correct something in red ink, it's going to say basically this is what we think now. So this is still true today. He said that atoms of a given element are identical in size, mass, and other properties. So he says every single hydrogen atom has the same mass, the same size, same properties. Atoms of different elements, different size, mass, and other properties. That's right. A hydrogen and oxygen atom don't behave the same. Today, we know that this is a little bit different. Okay, can anyone think about what that might be called? You know?
They have isotopes.
Isotopes, perfect. Okay? So today, we know that isotopes of the same element can have different masses. And we're going to expand on that in a little bit. So don't worry if you're not sure what an isotope is just quite yet. Okay? So his theory is in partial sections correct on that part. Atoms of different elements do differ in size, mass, and other properties. Atoms of the same element don't always have the same mass, same properties, same size. Okay, so we have something called isotopes. The next part of his theory said atoms cannot be subdivided, created, or destroyed. That's close, but we know that today we have man-made elements. So that means we've created this matter. Okay, we can split atoms now to look at protons, neutrons, and electrons. And we know now that there are smaller parts to the atoms, right? Subatomic particles, which are protons, neutrons, and electrons. Okay, so the last 2 points of his theory are still true today. So we're going to look at basically the discovery of the electron. Okay, a guy named J.J. Thomson did an experiment. And he found out that no matter what type of metal he was examining, they always gave off this negative charge. Okay, and it was always the same amount of negative charge. So it didn't matter what type of metal he was testing or what type of metal he was examining. They gave off this same amount of negative charge. And he began calling these particles that were giving off this negative charge electrons. Okay, that's how they got their name. So from this guy named J.J. Thomson, and he did an experiment with metals. We're not going to dive too much farther into the experiment that he did, but you do need to know that he was the guy that discovered electrons. So he was able to conclude that all metals have this electron or this negative charge, but he concluded through his experiments that every other element therefore must have these electrons also. Okay, looking at the charge and looking at the properties of other elements, he concluded that all elements must have these particles called electrons, these negatively charged particles. Okay, he didn't discover this, but later trials discovered that the mass of the electron was 9.103 times 10 to the negative 31st kilograms. So a really, really, really small mass. So small that when we are calculating the mass of an element, we don't even consider the mass of the electron to be in the mass of the element at all. If we're measuring the mass of a single element, we don't even consider the mass of the electrons. They are so small and so insignificant, they do not affect the mass whatsoever. Okay? So, we looked at these atoms and we looked at the electrons. We know that electrons are negatively charged, but not all of our elements are negatively charged, right? So that means there has to be something that balances that negative charge, okay, called the proton. And protons have what charges? Positive, right? Protons have positive charges. Okay, so we know all of our elements have electrons, which are negative, but we know most of them are neutral at room temperature, at their base state. They're neutral atoms. So there has to be something to counteract that called the proton. Okay. We also know that electrons have so little mass that it doesn't affect the element at all, so something has to be contributing to the mass besides the proton. And so what else contributes to the mass of an atom? A neutron. Good. And neutrons have what charge?
Neutral.
Neutral. They don't have a charge, right? Their charge is 0. This is where the experiments get a little more interesting, I think, is when we discovered the nucleus. Okay, so this guy named Ernest Rutherford started looking at where these things might be located within the atom, right? Where might these subatomic particles be located? And so he took this sheet of gold foil and bombarded them or rushed them with these things called alpha particles. Okay, and what alpha particles are, they're positively charged particles 4 times heavier than hydrogen. Okay, so they are positively charged and they have an atomic mass of 4 AMU. Okay, but the important part to understand here is that they are positively charged. Okay, so he has this sheet of gold foil and he starts pushing or tries to push these alpha particles through that sheet. And he wants to see what the effect is if they're going to come out the other side. Are they going to go in straight lines? What are they going to do? Okay. His expectation or his hypothesis was that they were going to pass right through that gold foil, with no deflection, right? He was imagining them going through in straight lines. Can we visualize what's happening there? Okay, can we envision those particles just going right through that foil with no deflection? They're not changing directions at all. They're going to be able to pass right through that foil. So knowing what we know about positive particles and knowing what we know about what's inside the nucleus of these gold atoms in this sheet, what do we think is probably going to happen to some of these particles that are flying through there? They're going to bounce, right? Because what do we know about positive on positive?
They don't.
Yeah, they bounce apart. Okay, they deflect. They do not attract one another. Okay, so this is kind of what he was expecting to happen. Okay, he was expecting these positively charged particles, or these alpha particles, which is in green, to kind of pass through here with little or no deflection, kind of basically just go straight on through there. Okay, this was Thomson's model of what he thought the atom might look like at that point, but this is kind of where we thought we might be going, right? Have a pretty simple path through there. most of the particles did just that. Most of them slid right through with kind of no problem. They avoided the positive charges of that gold atom. Some particles were redirected or deflected right at the source. So as soon as they hit that gold, they deflected back. Okay, so some of them went right through, no problem. Some of them deflected or got redirected in terms of their direction. So Rutherford examined kind of why he thought that might be, and he concluded that there must be a small positively charged region at the center of each atom, right? There has to be some region there that's got a positive charge that's deflecting these alpha particles, right? So I'm throwing in a positively charged particle, and it's got to hit this positive region for it to start bouncing back. What do we know that dense positive region is at the center of the atom? What's that called? Nucleus. The nucleus. Okay, he named it the nucleus. The center. So he kind of ran with this discovery of the nucleus, and he built a new model of what he thought the atom looked like. Okay, and it's called the Rutherford model. Okay, and I'll show you a picture of what the Rutherford model here looks like in just a second. But he suggested basically that there was this nucleus in the center, and that electrons just orbited, or they went around that nucleus, kind of like planets orbit. Okay, so his model is also called the planetary model, because it does look similar to a planet, okay, with some moons orbiting around there. What this leads to, having this dense region and then the electrons orbiting, is that most of the atom is actually empty space. So that's why he thought those alpha particles were able to just slide right through, right? They were hitting that empty space and they could go through with no problem. That's what he was envisioning, okay? So he discovered, he didn't discover, he built or drew or concluded with this planetary model, or the Rutherford model, okay? And let me show you what that looks like here in just a second. But I'll give you some time to get this written down. Right. So here is our basically source that's sending out these alpha particles. Here's our gold foil. Here's what he expected to happen, right? They passed right through. And that's where they're passing through, is that empty space that he's predicting. These guys are what threw him off. Right? These three that deflected different places. That means those alpha particles must have come in contact with what? The nucleus, right? They must have hit that nucleus of a gold atom and then been deflected, because we know positive on positive reject each other. So that's what happened. Those three threw him off. Obviously more than that in real life, but those particles that had been deflected are what made him now discover or rethink this whole model of the atom. Okay? Here's another picture of what was happening, okay? So this is more of what he thinks the model looks like, and here's an example of the planetary model. So this you need to have a picture of in your notes, because you need to be able to distinguish between these different models that we're going to talk about. Okay, so the Rutherford model has a dense nucleus at the center and then orbiting electrons. Okay, so he kind of thought electrons stay in this path, they're going to float around, but all this empty space right here was where those alpha particles were able to slip through, right? Didn't come in contact with an electron, which it wouldn't have made a difference if they did, and didn't come in contact with the nucleus. Okay, so the nucleus is made up of two things, protons and neutrons. Protons have a positive charge and a AMU, or a mass, of 1. Does anyone know? Oh, we already told you right up there. AMU stands for atomic mass unit. So the proton has a mass of 1 AMU. What's the mass of a neutron? 0 charge. But it contributes to its mass by 1 also. Okay, so protons and neutrons have the same relative mass. Okay, they each weigh 1 AMU. Have a no charge. No, they have no charge. Okay, I have typo there. No charge and a mass of 1 AMU. So if neutrons have no charge and protons have a positive charge, how do they stay together? How do they stick together? What do you think?
Isn't it something like, not really gravity, but something that's kind of like essentially gravity, like sticking them together?
Yeah,
Like they can't move?
something like that. Yeah, they're called nuclear forces. Okay, nuclear forces. They keep that proton and those neutrons held together because according to their charges, they have no reason to stick together, right? Positives don't stick to neutrals. They don't have any reason to stay together. So they have something called nuclear forces, which are very, very strong. Okay, what differentiates elements from one another? Their mass, their number of electrons, what is it? The number of protons makes each element different. Okay, so as we move on the periodic table, the atomic number is the number of protons, right? So atomic number is the number of protons, and that gives each element its specific properties. It's not the mass, it's how many protons that element has. So if we change the mass, no big deal, really. If we change the number of protons, that means we completely change that element's identity. It becomes a new element, right? Okay, so the atomic number is sometimes labeled as a Z on a blank periodic table, and it's giving you those values. Atomic number is usually at the top on the periodic table, right? It's usually in the top box. Isn't that true for your periodic table as well? Yeah. Okay, so carbon has an atomic number of what? 6, right? Carbon has 6 protons. If I take a proton away from carbon, is it still carbon? What is it? Boron, right? If I take a proton away, it's boron. If I add a proton, it's nitrogen. Okay, good. So for individual elements, the atomic number never, ever changes. Ever. Never. Some of you will still try to tell me that protons can change. No, they cannot. Okay? For neutral atoms, it also tells us the number of electrons. So if the protons and if the protons and electrons match, that means it's a neutral atom. All atoms on the periodic table in their base states are neutral. Okay? So if I ask you for just simple phosphorus, how many electrons does phosphorus have? You would tell me 15, right? Because that's the same as the atomic number. So when an atom is neutral, protons and electrons should equal each other. Okay, neutral means it has no overall charges. And we're going to get into charged particles here pretty soon, but for something that has no charge, that means protons and electrons must equal each other. Okay. Every atom of the element has the same number of protons. They do not always have the same number of neutrons. Okay? So if I change the number of neutrons, what is probably changing? The atomic number or the atomic mass? Atomic mass. Okay? So different number of neutrons. Atoms of the same type of element that have different numbers of neutrons are called isotopes. Okay? And I'll explain what this means here in just a second. Okay? But atoms of the same element can have different number of neutrons. They can take on different masses. So I can have a carbon that has a mass of 12. I can have carbon that has a mass of 13. I can have carbon that has a mass of 11. Okay, all that is there is differing neutrons. It's not differing the protons at all. All carbon atoms will have 6 protons. We might have 6 neutrons, we might have 5 neutrons, we might have 7 neutrons. It can change. Okay, and those are called isotopes. So isotopes are atoms of same element with different masses. Okay, that's just abbreviating what I've been talking about for the last minute. Okay, so let's look at some isotopes of hydrogen here. This is regular hydrogen right here. 1 proton, 1 electron. What is the atomic mass of hydrogen? 1. Does it have any neutrons? No. This H2 is called deuterium. 1 proton, 1 neutron, 1 electron. Okay? The only thing that changes between H and H2 is that extra neutron. Okay? The only thing that changes between these three is that we add one more neutron here. Okay, so 2 neutrons, 1 proton, 1 electron. Now I need to make a distinction. This is not H2. That's not, these two things are not the same thing. This is 2 hydrogen atoms bonded together. This is an isotope of hydrogen. Okay, so this one right here might also be labeled H-2. Okay, that's telling us that the atomic mass of that hydrogen atom is 2. Okay, this tells us that 2 regular hydrogen atoms are bonded together. So there's a difference in how we write those things. Does that make sense? Okay. So mass number and atomic mass are the same thing. Mass number and atomic mass, same thing. It's the neutrons plus protons in the nucleus of any atom or any isotope. Mass number and atomic mass are the same thing. You'll hear me say atomic mass more often. Your book says mass number. Okay, so I put both. These are a couple ways that you can basically show that you're talking about isotopes. So using this notation right here, which is called hyphen notation, which you don't really need to know the name, you just need to understand what this is telling us. Okay, this right here is telling us uranium dash or hyphen 235. That dash tells us that the mass of that uranium atom is 235. Does that match what's on the periodic table here? Where's uranium at? 238. Uranium is mass number 92. So if you look on your periodic table, it says that the atomic mass, or the average atomic mass, is 238. This particular isotope of uranium that we're looking at has 235 as its mass. So that means this isotope contains 3 less neutrons than the average that we see here. Are we on the same page with isotopes a little bit? Okay. Okay. If we're ever trying to find the atomic number of something, all we do is look on the periodic table for the number of protons and the number of electrons. That tells us the number of electrons in a neutral atom only. So if I ask you for the atomic number of zinc, you're going to tell me what? 30. And if I ask you how many electrons is in a neutral zinc atom, what are you going to tell me? 30. Good. Right? Protons and electrons are the same if the atom is neutral. I think everybody's good there, right? Okay. If I ask for the atomic mass of zinc, you're going to tell me what? 65.38. So the atomic mass is always the number of protons plus the number of neutrons. Why is it that we could have a decimal point for our atomic mass if we have protons plus neutrons? Can we have part of a neutron or part of a proton? Why do you think we have a decimal point then? Yeah, Cece, what do you think?
Sometimes it's an average of isotopes.
That's exactly right. Okay, Cece said it's an average of multiple isotopes. That's exactly right. So zinc might have 6 different isotopes that could exist in nature, right? It might have 6 different versions of zinc. If we take the average of those versions, that's what we're seeing on the periodic table for our atomic mass. Okay, so one might occur 98% of the time, and the other 5 might occur splitting that other 2%, but they still have to be built into the average of the atomic mass of that atom. Does that make sense? So if we see a number like carbon, which is 12.01, that means carbon 12 is probably a really common isotope, right? Because it's so close to 12. Okay? And if we see something like germanium, 72.63, that's telling us that we probably have a couple isotopes that are pretty common, right? Because it's kind of split down the middle. Does that make sense? Our atomic mass is close to 72 and close to 73. Do we see the relationship between that? Okay. Good. All right, we know how to find neutrons from the atomic mass, right? We subtract. Okay, good. I'm not going to go over that because I think you know how to do that. Okay. Now we're going to look at our last thing for today called ions. Okay? Ions are any atom with a positive or a negative charge. Any atom that has a positive or a negative charge is considered an ion. And we have specific names for if something has a positive charge or if something has a negative charge. Okay, so if I have an atom that has more electrons than protons, do we think it's going to have a positive charge or a negative charge? A negative charge, good. A negative charge, and those, I'll give you the name for those in a second. If I have more protons than electrons, do you think it has a positive charge or a negative charge? Positive charge, okay. And realistically, we should always be thinking about charges in terms of electrons, not really in terms of protons, because the number of protons never changes. So if I have less electrons, if I'm missing electrons, that means I have a positive charge. If I have extra electrons, that means I have a negative charge. Okay, and the name for these, the name for an atom or an ion that has a negative charge is called an anion. Okay, so an ion with a negative charge is called an anion. Okay, so that's negative. Bless you. And an ion that has a positive charge is called a cation. So a couple ways to remember these. Cation has a plus sign right in the word. Okay, so it's a positive. Look at an example here. If I have a lithium with one less electron than its protons, what would my charge be? It would be lithium plus, right? Or lithium plus 1. So I'll write this a little bit bigger here. When we write anions, we write the element or the name, the symbol first, and then we write the charge up as a superscript. Right? So it goes up top to the right. And when it's a 1, either a negative or a positive 1, you could just list it like this, as just a plus. Okay, you don't have to include the 1 if the charge is a 1. If it's anything more than 1, you do have to include that. Okay, so if you see this right here, it's telling me that I'm looking at a lithium atom that has 1 less electron than it should. Okay, because it has a positive charge. Are we on the same page there? Okay, so if I have an oxygen with 2 more electrons than protons, what's my charge there? Negative what? Negative 2. Okay, so that might be written like this. Oh, negative 2. So we can't just say, oh, negative here, because that would imply that it's a negative 1. And that's not the case. We're missing 2 electrons. I'm sorry, we have 2 extra electrons, so we have a negative 2 charge.